Oh, welcome everybody. Welcome all of you to attend the channel here tonight. So this is our first channel about the physics, especially in high school physics. The topic is about the very basic idea on mechanics. Most of you, if you are secondary school student or high school students, you may find it very useful in clarifying some basic concept. I hope this will help you to get a very basic idea on the topic today. It is about the mass and gravity. Okay, now let's begin. This talk is about 30 minutes. Okay, so it won't be long. So first, now let me clarify one thing first. Okay, uh, what's the meaning of mass? Okay, we all know that mass is a measure of inertia, right? We all learned it before. How about the weight? Now, weight comes from the gravitational force, okay, of the Earth. So normally we write weight is equal to mass times mg, right? Now, so as you can see, it is a scalar, right? It has only the magnitude. And for this one, it is a force. So beside magnitude, it has the direction. Now, all students should know this about this very basic idea of scalar quantities or vector quantities, right? Now, how about the situation here? Now, suppose we draw a circle to represent the Earth. Now, we all know that the Earth is rotating by about its own axis, okay? Each day, 24 hours. We call this the angular velocity is equal to omega, right? Now, suppose there is a person, okay, situated here, right, at the North Pole. Now, normally in the classroom, we told students about how to find out the weight of this person, okay, at the North Pole. Very simple. We just draw the force diagram, okay, in here. Now, we get the gravitational force from the Earth. We call this Fe, right? Now, if this body is in free air, then this is the only force acting on it, okay? This him or her, right? Now, we all know that the force is equal to the gravitational force acting on this person. Now, suppose we call this the radius of the Earth is Re, then we get this formula, right, from the gravitational force. Now, if we rearrange it, then we get this. Normally, we denote it as G naught, the gravity, okay, due to the Earth, right? Now, this equation is valid, okay, when the person is at the North Pole. How about the South Pole? Now, we get the same. Suppose I draw the person here, right? Now, the head is acting downwards, right? Now, there's only one force acting on this body, the same Fe. So we get the same formula here, right? So at the North Pole and the South Pole, we get the gravity or the weight, we call this. The weight comes from the gravitational force from the Earth, right? We call this the weight equal to mg naught, okay? And we call this the gravity due to the Earth, right? Now, what happens? Now, normally in the classroom, we just ignore it. Suppose here, right? Now, many students ask this question. Suppose there is a person situated at the equator. Okay, this equator, right? Now, when we draw the force diagram, Normally, we draw the same. Yes, there is a gravitational force acting on this person. We draw Fe, right? And we use the same formula to denote it, right? But of course, it is wrong. But normally, we do not want to discuss this in detail. Why? Because it involves a very important concept. It spends some more time to grasp the concept. So in this talk, I'm going to tell you about why we cannot use this formula to denote the gravity or the weight, okay, acting on this person. Now keep in mind one point, very important one thing is, the Earth is rotating about its own axis, okay? Now similarly, if the person is situated here, right, at the equator, this equation also, okay, at the opposite side, this equation also is not valid to denote the gravity acting on the person. How about the person is situated here, right? The situation is more complicated. So now here, I want to introduce a very important concept before we going to find out the actual weight acting on this person. Okay? This equation is not fully describe the situation here, right? Now, before we go on to find the real weight acting on this person, okay, at the equator. Now, let's recall a very important concept about the Newton's law. Okay, now, we have learned all Newton's law in mechanics. Now, we have the first law, second law, and third law, right? But here, right, we have the first law, second law, and third law, okay? Now, many students forgot one thing, the condition in which Newton's law is held. Now, what is the condition for the Newton's law to be true? Now, we have a very important concept about inertial frame. Inertial frames. Now, what's the meaning of inertial frames? Now, we call the frame of reference. That means when an observer tries to observe the movement of an object, we call this the observer, right? But the observer has to be in a frame or coordinate. We call this inertial frame. Now, under which condition Newton's law will be valid? Now, remember one thing. If the frame is at rest, or if the frame is moving at a uniform velocity. Now, under these two conditions, Newton's law is valid, okay? That means the first law, second law, and the third law. But how about the situation we just mentioned before? Now, we go back here, right? Now, notice one thing. For the person, okay, at the North Pole, or the South Pole, now, this person, okay, is stationary because the person is at the vertical axis of the Earth, right? So there will be no movement of the person, okay, at the North Pole here, right? So the equation here, that means the second law, F is equal to ma, is valid, okay, for the person at the North Pole and the South Pole. Because why? Because they are abreast. And it is an inertial frame. How about the person, okay, at the equator? Now, you have learned the circular motion. Now, the person at the equator will have a circular movement, okay, about the Earth's surface, right? So, for the person at the equator, it is not at rest. Also, it is not in a uniform velocity. Why? Because his velocity will change, okay, according to the position of the person, okay? Now, we say that this person will have an acceleration towards the center, right? So, here, for the person at the equator, now since the person is moving, okay, along the circle here, we say that there will be a centripetal acceleration, right? AC towards the center of the Earth. So, since this person has an acceleration always towards the center of the Earth, right? So, we can not use Newton's law, i.e. F equal to ma on the person. Now, what happens when students try to use the Newton's law, F equal to ma on this person? The student just ignore the fact that this person has an centripetal acceleration towards the center of the Earth. So, if you ignore this one, we'll get a wrong answer for the weight of the person here, right? So, if we ignore the centripetal acceleration of AC here, right? Then we just draw the force diagram. Here, now, I draw the force diagram. There will be a centripetal force F G, right? Acting on this person due to gravitational, right, force from the Earth, right? And we write the same thing, our Earth square, right? And we will get the same formula as before. And we think that the gravity at the equator is also equal to G0. Why? Because we apply the F equal to ma to this person, regardless of there is an centripetal acceleration towards the center of the Earth. So, it is a very typical common mistake made by students, okay, when they try to tackle or solve the problems involving the gravity on the surface. So, if we cannot use Newton's second law, then how we can find out the gravity? So, in order to solve this problem, actually, the method is not so difficult. Now, suppose here, right? Suppose To save time, I draw a diagram first here, right? Here. Suppose this is a small car, right? Or a train, right? It is at rest. So we call this an inertial frame. That means if you are inside this train or cart, okay, etc., right? When you do the observation or do the experiment, then you can apply the F equal to ma, no problem, okay? Because it is an inertial frame. Newton's law will hold, right? How about in this situation? For the train or the car, okay, moving with uniform speed. Now, since it is moving with a uniform speed, Newton's law still hold. So you can still use F is equal to ma. No problem. Okay? How about the situation here? Suppose the train or the car move forward with an acceleration a. Like you take a MTR, when the MTR start moving forward, you move backward, right? So according to the person in the train, you experience a force acting backwards, right? Due to what? Due to the change of the frame of the train. So when the frame is moving forward, for the person inside the train, you may regard there is another force, F, acting on this person. And this force arise due to the acceleration of the frame is called fictitious force or apparent force. So if you want to use Newton's second law or Newton's law, make sure that the person or the body is an inertial frame. Now, since the train is moving forward with an acceleration a, we cannot apply Newton's law here. Why? Because now, as you can see, there is no force acting on this person, even though the train is moving forward with an acceleration a. But as you can see here, right, this person or this body will move backward. Very strange. Why? Because actually the train is moving forward with an acceleration a. Therefore, in order to describe this situation, we say that, because this person is accelerated backwards, there must be another force acting on this person. But this force is not due to actual force. No, not actual force. No physical origin. No. This force arises mainly due to the change of the frame, i.e. the acceleration of the frame. So, how to make use of the fact that there is a fictitious force here, right? Now, in order to use the Newton's law, okay, either first law, second law, and the third law, we try to add another force in opposite direction to the acceleration of the frame. So in this situation, if the train is moving forward with an acceleration a, we add another force due to the change of the frame here, right? To the left. That's apparent force F. F is equal to ma, equal to the acceleration of the frame, acting leftward. If we put a negative sign here, we will get the force acting backward. Now, by inventing this apparent force due to the change of the frame of reference, now we can now use the Newton's second law. Now, Newton's second law can be used now. Okay, no problems. Okay? Now, so when you return to the previous situation here, right? Now here, if you return to the situation here, right? Now, let me put back the diagram, okay? we have just drawn before. Now notice, this person has an centripetal acceleration towards the center of the Earth. I repeat, so the frame of reference referred to this person is not an inertial frame. So we cannot use Newton's second law. So in order to use the Newton's second law, we need to add, very similar to the situation in the train, we add an apparent force or fictitious force towards the negative direction of the acceleration of the frame. So here, so for this person, beside this force Fg, in order to use the Newton's second law, F equal to ma. Okay? We need to add another force. We call the apparent force acting on this object. So since the centripetal acceleration AC is towards the center of the Earth, so we need to add another force acting on this person. I draw the arrow here, a big arrow. This one very thick arrow, right? Very thick arrow. Now, this force arises due to the change of the reference, right? And we call this another small f. Now, by inventing this force, we can now use Newton's second law. Now, therefore, for the person here, right? Now, the total force, now for Newton's second law, now we draw, maybe I draw another diagram so that you can see clearly. Now, this is the person, right? Now, remember, this person is moving in a circle along, okay, the surface of the Earth, right? So it has a centripetal acceleration AC towards the center of the Earth. So it is a non-inertial frame. So in order to make it become an inertial frame, non-inertial frame to inertial frame, we need to add an apparent force equal to m minus AC in the opposite direction of the acceleration of the frame of the reference, right? So now by adding this apparent force, we can now use the Newton's second law. So by F is equal to ma. Now we have the gravitational force F and the apparent force, okay, acting radially outward. So the total force will be gmm r Earth square Fg, right? Minus a very small force m, the centripetal acceleration. Now remember, the centripetal acceleration is equal to of Earth omega square, right? So we can substitute, right? Into this formula. So now this is small f, right? So we cancel the m. So the expression a is equal to gm r f squared minus r f omega squared. Normally we call this one. Our Earth is equal to the radius of the Earth, right? So we get a very small negative terms here, right? A very small negative terms here. This negative terms is due to the non-inertial frame of reference, okay, of the person. But because we want to use the Newton's second law, so we need to add this apparent force to it. This arises from the apparent force. So here, right? So we get a very important concept about non-inertial frame to inertial frame. Now, so here, you can see that this value, we call this the G, okay, at the equator, is less than G naught, right? Okay, now, what happens when the person, okay, is not either at the North Pole or at the equator? What will be the value of the gravity acting on the person? Now we can use the same argument. Okay, now I draw another diagram so that you can see more clearly. Now suppose here, right? Now I will not do the mathematics because it involves some binomial expansion and some approximation. It is rather demanding for high school students. But I will tell you the force diagram and how to solve it. If you like, you can solve it, right? Okay, now, here, suppose this is the Earth. Suppose this is a person, okay? Somewhere like this, right? And the angle with the equator is equal to theta. Now, we use the same argument. Now, first, the force acting on this person from the Earth is Fg towards the center of the Earth. Fg, right? Fg. And now, since this person is at this position, it also have a circular motion about the vertical axis of the Earth. But the circular motion has a smaller radius r from the axis of the Earth. The radius r is smaller. This r is smaller. But it doesn't matter, right? Now, it also has an centripetal acceleration, AC, towards the axis of the Earth, right? Now remember one thing, I repeat again. Now, since this person is moving along this horizontal circle, it is a non-inertial frame. So we cannot use Newton's second law, right? In order to use the Newton's second law, we try to make it into an inertial frame. in order to make it into an inertial frame, we need to add an apparent force, right? Like before. So here we get another, we add the apparent force, okay, in the opposite direction of the centripetal acceleration of AC, okay, this small f. So now by adding this small force F, we can now use the Newton's second law. Now, since the person has two forces, so as you can see, if you draw the diagram, by adding these two forces, by drawing parallelogram, you can see that the actual G is somewhat pointing towards this direction. It is not pointing exactly through the center of the Earth. It is slightly different, right? Downwards, as you can see. So I will not do the mathematics about how to calculate the value of this G. You can use the cosine law to do it. Okay, now, so up to now here, right? We have tried to change the non-inertial frame into inertial frame in order to use the Newton's second law in order to find the gravity of the person, okay, at various positions on the Earth's surface. Now, how about this one? Now, because this concept is very important, so make sure when you try to apply the Newton's second law or Newton's third law or first law, make sure the object is inside an inertial frame, or else you'll get a very weird answer. Normally you'll get a wrong equation, very strange answer, okay, because you forget one thing, because Newton's second law is not hold in this situation. Okay, now let's here ask you two questions. Now you understand what's the meaning of gravity, okay? You know it. The gravity at the North Pole is called the G0, right? At the equator is equal to R Earth omega square, right? Somewhat like this. So the gravity, okay, here on the Earth's surface at the equator is smaller at the South Pole or the North Pole or the South Pole. So here, suppose, now you get the basic idea here. Now suppose you are going to sell or buy diamond, okay? Will you use mass or weight? Now, if you understand what I'm talking about before, you can see that if you use the weight, that means the Newton's second law, you get different value, okay, of the gravity on different positions on the Earth's surface. So we cannot use weight. Why? Because the weight changes with the position, okay, on the Earth's surface. So we need to use mass. But how to find the mass of the diamond on different positions? Very simple, okay? We use the beam balance, right? Why? Because now we use a long mass M2. By using the M2, this long mass, we try to balance the lever, right? By using the moment, okay, the formula of the moment, we get the mass of the diamond on the left hand side. Okay, it's very simple. So if you have gravity, then we can use this method to find the mass of the diamond instead of using the weight of the diamond, okay, on the Earth's surface. Now you should have learned this formula, okay, before, right? So because it involves the gravity actually, but the gravity will be cancelled out. So the different value of the G on different position doesn't matter, okay, in finding out the mass of M1 here, right? But how about the situation here, right? In this situation, how about if you are in a spaceship, right? You want to sell or buy diamond in a spaceship, but in this space, there is no gravity, okay? We cannot use the balance or the lever system, right, to find the mass of the diamond. How we can find the mass of the diamond? Now, if you are in a position there is a gravity, then you can use the beam balance. By balancing the right and left hand side, you can find the mass of the diamond by cancelling out the gravity on the left and the right hand side. But if there's no gravity, how you can find the diamond or the mass of the diamond? Now, remember, we have two very basic ideas, okay, in mechanics: conservation of energy and conservation of momentum. So if there's no gravity, how we can find the mass of a body? Now we have no choice. We have to make use of at least one of the principles: conservation of momentum. Now, we try to imagine the two masses, they are holding together by a spring. You try to compress it. Now, initially, it is at rest, so the total momentum is equal to 0, right? Now, you try to cut this spring. The mass m1 and m2 will move in opposite direction, right? But due to conservation of momentum, you can see that the momentum after the string is being cut is also equal to 0, equal to before. So you can calculate the mass of m1 if we know the mass of m2, and also if we can measure the velocity of u1 and u2. Okay, it is very easy to measure the velocity of the two objects. So if there is no gravity, then we can use this method to measure the mass of an object or the mass of a diamond. Okay, so although this example, question 1 and question 2 are very simple, but it involves a lot of the concept, okay, in physics. So I hope in this talk you can have a more understanding on the gravity, and also about in what condition we can use the Newton's second law. Okay, if you have any question, you are welcome to leave your question or your comment, okay, in the YouTube channel. Okay, next week I will discuss another topic about the misconception, okay, in another topic of the physics. Okay, see you next week.